it's time for our next talk. Our speaker is Wynne from the University of Colorado Boulder.
Great. Thank you for the introduction. Thank you for the organizers for having me. Today I'm going to talk about something called clonoids. So if you've heard of a clone before, then you may think there's some connection between clones and clonoids. Of course there is. So first, what is a clone? So if we start with an algebra A with some basic operations, Ni, of some arity, say Ni, we can think of these as just functions from powers of A into itself. Then from these basic operations of our algebra, we can form new operations, which I'll call term operations, by composition. So if G is one of our basic operations, as well as F1 through Fn, then if the arities match up, then we can form a new function from our basic operations H and F1 through Fn. So G is not a basic operation of our algebra, but it is a term operation. So I'll denote by CLO of A the term clone of A. So the clone of all the term operations of the algebra A. So in general, if we have a subset of the functions from powers of A into itself, we call this a clone if it first contains all of the projections and also is closed under composition whenever the arities make sense. So for example, if we have a vector space, so here F is a finite field, or any field really, so F is a field, then we can think about this vector space. Then what is the term clone? These are all of the functions that we can form from the basic operations, addition, negation, the zero vector, and unary scalar multiplication. So then the term clone, of course, is just all of the linear combinations we can form from these basic operations. And another example, if we have the integers as a ring with addition, negation, and zero, constant zero, as well as the product, constant 1, then all of the operations that we can form from these basic operations, the term clone of this algebra would just be all of the polynomials in however many variables over the integers. So a clone we can think about as the term clone is just all of the functions we can form from the basic operations. So now what is a clonoid? So if we start with an algebra A and another algebra B, then clonoid is a subset of functions from powers of the first algebra into the second algebra with some closure properties. So first, if we first do operations of A and then do a function from A into B, then this new function that we get will remain in our clonoid, and as well as if we first map from powers of A into B and then do some operations in B, this new function that we get will be again in our clonoid. So I'll say that C is clonoid is closed with respect to precomposition by the term functions of A, as well as postcomposition by the term functions of B. So an example. So if we start with A being the abelian group with 3 elements, and B being a lattice. So originally B was also another abelian group, but I figured I might as well try to hit as many letters of blast as possible. So at least I got a lattice in there. So if C is a clonoid from A to B, then say F is in our clonoid, a binary function in our clonoid, then we can form a new function by replacing our first variable, say x1, with the new function x1 plus x2. So we're substituting this term function x1 plus x2 into our first variable, and then we're substituting the constant 0 function into our second variable, and then similarly we can substitute into our first variable 2 times x1, and into our second variable 2x2 plus x3. So inside, these are both these are term functions of A, of the group. And then we can form a new function, G, so that's of arity 3, that takes this f of x1 plus x2 and 0, and meets it with f of 2 times x1 and 2 times x2 plus x3. So we first do some So we have a function f, we first do some operations of A, then map into B, and then do some operations of B. This new function that we get remains inside of our clonoid. So just some notation, I'll just denote by angle bracket f, the clonoid generated by f, so the smallest clonoid that, from A to B that contains the function f. Okay, so if you know about clones, then you know that these are determined by relations, and similarly, clonoids are determined by pairs of relations. So if we have a relation R, an n-area relation on A, and S, an n-area relation on B, then we denote by pol Rs the set of polymorphisms of the relational pair R and S. So this is all the functions where if we map F, if we map tuples of R, then the resulting tuple after we map into B is in the relation S. And so this theorem by Cruzeiro and Voldish says that whenever we have algebras A and B with A a finite algebra, then these two statements are equivalent here. So if we have a clonoid from A to B, then actually this clonoid is determined by a whole bunch of relational pairs, and conversely, the polymorphisms of a relational pair will in turn give us a clonoid exactly when these relations are subalgebras of A and of B respectively. So, an example of this, so let's take A to be the integers modulo 9, and B to be the integers modulo 2. Then here I'm thinking of 3 times Z9 as a unary relation on A, and 0 as a unary relation on B. Then the polymorphisms of this relational pair are all the functions that map 3 times Z9 to 0. So they're constant on 3 times Z9. So if all the inputs come from 3 times Z9, then the output will be a 0 inside of Z2. Another example, the same A and B. If we take the first relation to be equivalence modulo 3, thinking of that as a binary relation, and the second relation to be the equality relation, then the polymorphism, the set of polymorphisms of these two relations is then all the functions that are constant modulo 3. Okay, so first, I should maybe mention, so these clonoids are subsets of functions from powers of A into B, and so a priori there could be uncountably many clonoids from one finite algebra to another finite algebra. So a priori there could be continuum many clonoids between a finite algebra and another finite algebra, and for the setting that I'll work in for the rest of the talk, it turns out that there aren't continuum many. So theorem by Erhard Eichinger, as well as Peter Meyer, says that if we have a finite algebra A and a finite algebra B, where B is a Malsev algebra, so this has a Malsev term, then actually the clonoids from A to B are finitely related. They're related by just finitely many relational pairs, and then from there we can get that actually they're given, this clonoid is given by just a single relational pair. So of course now, since clonoids then are determined by a single relational pair, where B has a Malsev term, then this gives us that at most there can be countably many clonoids. So in the case where B is an abelian group, then a finite abelian group, I should say, then actually the number of clonoids between A and B is at most countably many. Okay, so in some cases, we actually attain this upper bound. There is actually as many clonoids as there could be from that past theorem. So in the case where A and B are finite abelian groups with a common prime divisor, then the number of clonoids between A and B is actually countably infinite, so it's as big as possible. And so the idea behind this is, I'll just sketch the proof idea where A is just the integers modulo P, and B is also the integers modulo P, just with addition, so just the abelian group. Maybe I should mention that this sort of special case of this theorem was already proven by Sebastian Kronecker. So he characterized all of such clonoids between A and B, but I'll just use this sort of subset just to sketch the idea. So I'll define this function fn, which takes in inputs x1 through xn and outputs the product x1 times x2 times up to xn, where this product is just the normal product on ZP. Then this chain here, I claim that this is actually an increasing chain of clonoids. So the clonoid generated by F1 is strictly contained in the clonoid generated by F1 and F2, etc. And so how do we see this? Well, one thing to notice is that for this function Fn, if any of x1 through xn are 0, well then the output will be 0 inside of ZP. So Fn is a zero absorbing function. Whenever the one of the inputs is 0, the output is 0. But so if we look at the functions inside, say, the clonoid generated by F1 and F2 of higher arity, of arity greater than 2, well, it turns out that the only functions inside here that have this property of being zero absorbing are actually just the constant zero functions. And of course, that would not include, say, F3. So that shows that this is actually a strictly increasing sequence of clonoids, and so then we have countably many clonoids between A and B. And we can generalize this same idea to show that whenever A and B are finite abelian groups, or actually finite modules with a common prime divisor, then there's countably infinitely many clonoids between them. Okay, so now we'll look at the other case. What about if the two don't have a prime divisor? So first I'll start with this theorem by Stefano Fioravanti, which says that if A is the integers modulo P, and B is some abelian group, which is order coprime to P, a finite abelian group, order coprime to B, then actually the clonoids between A and B, from A to B, are generated by their subset of unary functions. So if we know what the unary functions look like, then we actually can figure out what are the functions in the clonoid of higher arity. And of course, if A and B are both finite sets, there's only finitely many unary functions between them, and so the result is that there are finitely many clonoids between ZP and some abelian group of coprime order. So how does the proof go? Well, we want to show that if we have some function of arity, say k, then we can generate from this function of arity k a bunch of unary functions, and then from these unary functions we want to reconstruct this function f of arity k. So that would show then that the unary functions generated by f in turn generate f again. So if we take some vector in zp to the k, we can think about the span of this vector as just a line through the origin, then we can construct from the unary functions generated by f, we can construct a new function which looks just like f on a single line and is 0 outside of this line. So we can interpolate this function on some line. So on each of these colored lines here, we can interpolate this function f, and then if we add all of these interpolations together, well then they will cover the entire zp to the k, and so then this would give us back f. Of course, they overlap with the origin, so we're finagling to deal with that, but other than that, then we can reconstruct f from these fv's. So the important thing is that from f, we can construct some unary functions. From those unary functions, we can reconstruct f. So that shows that for any clonoid, it's actually generated by a subset of unary functions. Okay, so then this leads to the question, what about for other pairs of abelian groups that are of coprime order? Is it still true that there are just finitely many clonoids between them? Well, unfortunately, I don't have an answer, but I have a partial answer. So this theorem now says that if we have A to be the integers modulo some natural number, so the cyclic group of order m, and B to be an abelian group of order coprime to P, then or order coprime to m, that should say. Yeah, this is a typo. So that should say that B is an abelian group of order coprime to m. Then the clonoids from A to B are actually generated by their n-ary functions, where here n is just the highest power of a prime dividing by n, dividing the order of A. So maybe first just an example. So if we take A to be the integers mod 2 and B to be the integers mod 3, then this theorem is saying that, so here m is just 2, and of course then the highest prime power dividing 2 is 2 to the power 1. So this theorem then says that these clonoids should then be generated by their unary functions. So if A is Z2 and B is Z3, then the theorem says f is generated by its unary functions. So from f, we can look at the unary functions that f generates. So these are exactly just f of x and x, so we can replace both variables with x, or we can replace one of the variables with 0, or both variables with 0. So we can get these four unary functions from our function f, and now we can rebuild f from these unary functions. So now here's the equation showing that f can actually be constructed by reconstructed back from these unary functions, and so inside of each of these unary functions is a term function of our algebra A, which of course is just a linear combination of variables, and then we can then take linear combinations of those new functions. So we compose on the inside with some linear combinations in Z2, and then on the outside with some linear combinations of Z3. So I wrote 2 inverse here. Of course, the inverse of 2 in the integers mod 3 is just 2 again, but I really just want to emphasize that what's really important here is A. What's all that we care about B right here in this example is that it's of order coprime to A, so we need that 2 here is invertible in B. Okay, so now I just wanted to sketch the idea of this proof, so of this theorem. So first, here's a simplified version of the theorem. So here m is just a prime power to p to the power n instead of arbitrary cyclic group of prime power order. And so our theorem says that the clonoids from A to some coprime B should then be generated by their n-ary functions. So the idea is again similar to what we did for when this prime power was power 1. We want to take an arbitrary function, decompose it, see what the n-ary functions that it generates are, and then reconstruct f from those n-ary functions. So first we're going to reduce to the case where f is 0 on the maximal submodule, or the maximal subgroup, p times a. And then from here we can interpolate f on some subset, so we can reconstruct a function that looks like f on this red box and is 0 outside of that red box. So on a times p times a to the power k minus 1, this function just looks like f. Everywhere else, this function is just 0. So we interpolate f in this region, and now we can do that same thing on a whole bunch of other regions. So if we take some subgroup of a to the power k that has this property that a to the k modulo n is isomorphic to a modulo p times a, then we can so essentially this is saying that n more or less looks like this red box here from the last example. Then we can reconstruct f from these functions that interpolate f on these regions. So we get now for each such n, we get a function that looks like f on this region n, and off of this region n, the function is just 0. And now it turns out we can cover all of a to the power k with such regions, but now unlike the case where we just had zp, they're going to overlap more than just at the origin, but we reduce to the case where there is 0 on the overlap, and so then again we can add these functions together to reconstruct f from these functions. So each function looks like f on its support and it looks like 0 everywhere else, but now they're all going to overlap here in this band region, but in this region already the functions are 0, and then so what that means is then we recover f from these fn's, and the important thing is that each of these fn's was already generated by not by f itself, but by the n-ary functions that f generates. So we start from a function f, we find the n-ary functions that it generates, and then we reconstruct f again. And so that shows then for any clonoid, we can look at all of the n-ary functions inside that clonoid, and then from those n-ary functions, we can reconstruct the clonoid. So that's the sort of the 5-minute version of the proof. And then of course, this gives us that since these functions are from a finite set to another finite set, there's only finitely many n-ary functions, and so again, then the total number of clonoids between these two abelian groups of coprime order is finite. So maybe I'll just mention that here. I just wanted to talk about the abelian group case, but really we proved this in a little more generality, and so we proved essentially an analogous theorem for finite modules with some certain nice structure, and the nice structure that we sort of had to settle on or deal with was we need that the congruent, or that the lattice of submodules is actually a distributive lattice. So for the integers modulo some natural number, we get a distributive lattice as it's a subgroup lattice, and so we can somehow generalize this to other modules of, again, coprime order. So we don't quite then have the full picture, but we're sort of almost on the way to showing that if we have, well, maybe, I'm not sure if it's true, but maybe if we have two abelian groups of coprime order, then always the number of clonoids between them is finite. So that's all I have for now.
He said you.
Okay, so yeah, nice talk, thanks. And do you have any? Can you prove anything about any cases where the first group is not the second group?
Yes. So actually, but I mentioned the case where A is just the integers mod p, and then in this case we have unary generation of the clonoids, and so it turns out that if in the first component we have any regular module which is a product of simple modules, then we get and the second algebra is again of coprime order, then we still have unary generation. So in this case there are finitely many. So maybe if we try to do the exact analog of this theorem, we might look at the abelian group, say zp times zp into some abelian group of coprime order. The analogous theorem might say that these are generated by their unary functions. This turns out to be false. So we can't super easily generalize this, but even in that case, I'm not sure if there's finitely many clonoids between, say, Cp times Zp into, say, Zq for some other prime.
How about Z2 plus Z2? In that case?
Yeah, so maybe it shouldn't be, but I just didn't drink enough coffee, I guess.
Okay. I was just wondering if you had some examples.
Yeah. So there's still some ezy examples that I still have to settle. Well, either they're not easy or I didn't drink enough coffee.
For clones, there's a lattice of clones. So the question is whether this notion applies here, and so looked at some of these lattices.
Yes, so it turns out that again the clonoids between two algebras will form a lattice. If we have a constant in our in the second algebra, then we have a smallest clonoid which just contains all of those constant functions. But in general, this lattice might have so the empty set would be the smallest clonoid, strictly speaking. So there's not necessarily non-trivial intersection between two different clonoids, but still we we get a lattice of clonoids, yeah. Is that the question? Okay. Yeah.
I have maybe two questions actually concerning the first question. So it sounds like you don't have any result that says like, oh, if it's finite for certain groups, then I can do something for the disease part. Because I mean, you're saying like there's no easy way that there's indeed plus EP, so there's no chance currently to see anything in that, right?
So not quite yet. If you consider ZP cross ZP as instead of a abelian group, if you consider it as a module over itself, over ZP cross ZP, then in this case, we do have an answer. But in the abelian group case,
maybe it's the definition of the clonoid of the beginning was a little fast for me. Just asking, so it sounded like that over Z, polynomials in variable x are allowed. So that would be something like x1 to the 3 or something like that. Is that possible? Or do they have to be linear and every variable?
So it just has to essentially be closed with respect to composition with the term operations. So if the term operations are just the group addition and negation and zero, then they would just be linear.
They would be linear. So
if we instead consider the ring, then
what does that happen? So I mean, there's two variations of this. Of functions below and very closure.
Yeah. So in that case, we have additional operations. If we add these additional operations to the source, so say we let A to be the ring, we add the multiplication on the integers mod n, then we have so in this case, I believe now this new lattice of clonoids will embed into the old lattice of clonoids. So essentially we have fewer clonoids in that case. So then if we have this finiteness result, then that's preserved.
In your example, the way in which you reconstruct f from its generated operations does not depend on f, right?
Yeah.
So
The proof of our theorem, I didn't really mention it here, but it actually is independent of the function f itself. So these functions are somehow uniformly generated. So, for example, so in this example, no matter what function f, binary function from z2 into z3, then this equation here holds. And so it's independent of the actual function f. Yes. So all of these results where I gave some sort of interpolation of the function is independent of the actual function itself.
Time for another question. Let's thank Patrick. The second part for tutorial in 6 minutes.
Those